to make sure you see at least the logic. We need these two things, probability of receiving a 0, probability of receiving a 1 before we go any further. With me? That's where I start these problems. And one other thing, it doesn't have to be just binary. You can have more. Y'all follow me? It could be trinary. You could have 4 different values. It could be a 1, a 2, a 3, and a 4 kind of deal. So you have to be, you always have to think about these things in terms of how you can really extend what we're talking about, the basic principle, to something larger. Okay, for this, I don't know what it is exactly. Probably have written it down. Does anybody have that?
0.398.
Okay. Now, here's how I get the next one. So the probability of receiving, the probability of receiving 1, we'll call it 1R, that's just going to be 1 minus this probability of receiving a 0. Now, we could get it by doing this same type of operation again, but you don't need it, really. Y'all follow me? So this is one last step. And what is that?
0.602.
Okay, they're close to the actual transmit and transmit 0, transmit 1 probabilities. Everybody with me? All right, now we've got that, the next thing we do is take a look at what they're asking. Be careful about these things because you can get confused. Come on, go to the next door.
Sorry, I normally open that door.
I'll open it. I mean, if anybody gets here, open that door and turn on the lights, whoever's first in the room. All right, now he asked for the probability
to receive 0 is transmitted as a 0.
All right, the probability. Probability. And this is going to be probability of a received 0. So we received a 0. And it's transmitted as a 0. It's transmitted as a 0. So we receive something, and we want to know what's the probability it's transmitted as 0. You all with me, class? Now this is the standard Bayes theorem thing. I'm going to put up here for everybody. Remember, if you take P of A times P of B given A, that's equal to P of B times P of, times P of A given B. That's Bayes theorem. And we talked about, we got it from a Venn diagram where we had the intersecting areas last time. Take a look at this. So what I'm going to do is take a look at this. Doesn't matter which one you call A and B, really. But if we take a look at this, I know whatever's on the bottom here, this is given, this had occurred. So I have to multiply this by the probability of a 0 received. Follow me, class? This is the way I'm doing it. On the other side, this is going to be the probability that a 0 was received given a 0 transmitted, and then it's going to be times the probability of a 0 transmitted. I don't care about the symbolism. If you want to say A is equal to 0 transmitted, B is equal to 0 received, you can do that symbolism. Y'all follow me? But I'm doing it this way. And you can choose however you want to do it. Does everybody understand the logic on this? All right, now, the one thing I have P0 received. I'm after this. And I have P0 transmitted. And I also know the error rate. Follow me on this? So if a 0 is transmitted, the probability that it's received as a 0 is 0.92. Everybody with me on this? I've got to make absolutely sure about this. This is the one, they look simple, but people stumble. I promise you, they stumble like crazy on these. So for this one, I want P0 transmitted, 0 received is going to be, and in this case, I'll put it up one time and I'll put the numbers in. P of 0 received, 0 transmitted, P of 0 transmitted over P of 0 received, and finally I'll put the numbers in. So probability of a 0 received given a 0 transmitted is
0.92.
Everybody follow me on this? I mean, sometimes interaction helps you remember it and see it. So it's 0.92. The probability that the zero is transmitted is 0.4. And the probability of zero received is all that, right? 0.398. What does that come to?
0.92.
0.92? Something, right?
46.
46? Is that right, class? Okay. That's the first part, that's A. For part B, I think I can do it right here. Is this probability a 0 or a 1 is transmitted given a 1 received?
Probability that received one was transmitted as one.
Okay. So this is basically that problem with the other value. So it's going to be probability. In this case, it's going to be a 1 is transmitted given a 1 received. And you can almost see this now. This is like the P of A over B, right? Whatever's down here, you know, you're going to multiply it by that probability on this side. Do y'all follow me, class? If it was probability of A given B, you'd multiply by probability of B here. And in this case, it's the probability that a 1 is received. And that equals the probability of a 1 transmitted. And then it's going to be times probability of a 1 received given a 1 transmitted. And so there's nothing tricky here if you follow the first part A. This should be a natural extension of that. So I'll just take this and divide it by probability of a 1 received and get rid of that. And that means probability of a 1 transmitted, 1 received is going to be equal to probability of 1 transmitted is 0. Anybody? Can you all read that? What's the probability of 1 is transmitted? Right here. Is this legible? 0.6, right? All right, if it's not, let me know. 0.6, probability that a 1 is received given a 1 transmitted? That's right. 0.95. And then it's over the probability of 1 is received, which,
0.602.
points, what?
602.
602. And that comes down to
0.9468.
now those numbers are close, and I want to say one thing. You'll notice you're going to have to take it out to 3 decimal points to make a clear point about this. Y'all follow me on this? So be careful with these problems because error rates are low. All right, the final part, C, is
The probability that any symbol is received in error.
y'all follow me? All right, how do you do that one?
Is it probability of a 1 received but a 0 transmitted, and then the opposite case too, like getting a 0?
Y'all follow what he's saying, class? So what he's doing is he's saying, well, the probability of an error occurring is the probability of 1 is transmitted, there being an error, plus the probability of a 0 transmitted, there being an error in that. Now that one is easier in my opinion. That should have been the first one, but nevertheless, part C, so the probability of an error is going to be equal to probability of, and this would be of a 1 transmitted, 0 received, times probability of a 1 transmitted, plus the probability of a 1 received given a 0 transmitted, times the probability of a 0 transmitted. I'm just writing it out for completeness here, to give everybody a visual on what I'm thinking. Everybody with me? All right, what's that going to be? Well, probability of a 1 transmitted and a 0 received is really the error rate associated with the 1, right? Do you agree with that? And that's 0.05 I think, yeah, times the probability of one transmitted is 0.6, plus the probability that one is received and a zero transmitted is going to be 0.08 times the probability of zero transmitted is 0.4, and what does that answer? Just, and then I got a few comments.
0.062.
Everybody agree with that? This is a good basic problem that shows you how to think about it. Here's the real confusing part. You got 0 here, 0 here, 0 received, 0 transmitted. I promise you, people will stumble around with those. They will mess it up because they don't have a clear feel for this, and that's a problem. All right, let me keep going. By the way, I didn't look at the weather today, but the weather that I looked at last night says today is going to be loaded with rain and thunderstorms all day today. Which isn't exactly what I had in mind for a Friday afternoon.
I'm sure the people here for the playoffs are very happy about that.
So what do they do with baseball? If it rains, they postpone, don't they? So the whole weekend it's raining. Am I not right? Or somebody's going to have to think this through, because
Yeah, it doesn't stop till Monday.
bad times are turning. I don't know. I really don't know what we're going to do.
They need to get one of those giant
Probably.
covers like the Coliseum had, where you could cover the whole field.
For a baseball field, think about it. What
Just a
What stadium in this country has for baseball indoors? Is the Astros indoors?
Rangers,
What is it?
the Rangers have one.
That is an enormous capacity. You have, I mean, the outfield goes to over 400 feet, right? Then you have the stands, and you have to have a dome that covers that whole thing. We're not going to see one, I don't think, not in my lifetime. Okay, the next thing I want to do, actually, that problem I thought, of all the problems I looked at in that section, that was the one I figured you'd trip over the most, because if you have 3 things, it can, I promise you, people get so baffled, but you have to see the first one well before you see the second one. All right, I want to do 1-7.3, the problem, too, on this one. And the reason I'm doing this is, I think this one is kind of weird, but it forces you to think in a way where anytime you're dealing with probability, you have to think of total possible outcomes, and you have to think about any type of thing where you have something can't happen, something can happen with a certain probability, and something will happen kind of deal. I'm not phrasing this the best way, but 1-7.3, go ahead.
Your candy machine has 10 buttons, of which one never works, 2 work half the time, and the rest work all the time. The coin is inserted and a button is pushed at random.
All right, 0, 1, 2, 3, 4, 5, 6, 7, 8. Boy, actually, what I should have done, I'll just think this was 9. There are 10 of them there. So 1 doesn't work. That one doesn't work. This works half the time, and this works all the time. So the probability of them working are 100%, right? Okay, now for this problem, what does it ask?
What's the probability that no candy is received?
Given that a coin is inserted, I don't think it says that, but it should have been. So if you put a coin in, what's the probability that no candy is received? Now, just think about this. It's the probability that this would be pulled, right? They're all equally likely. I don't think it says that either, but it assumes all these levers or whatever they are equally likely. The button's pressed, right? So there's 10 of them. It's pretty straightforward. For part A, really the probability of no candy is going to be just 1/10, and I think everybody sees that.
Would it be,
Or sorry.
because then two of the buttons work half the time, right?
I'm sorry about that, you're right. You're absolutely right. And I didn't say this, I'm thinking ahead. I should say it's the probability of this occurring plus the probability of this occurring times the actual payoff, or the probability of payoff times the probability of that occurring plus the payoff. I'm sorry about that, you're absolutely right. So it's going to probability of this occurring, probability, I'll call it a 0, plus the probability of a 1 times pulling that lever times getting candy is going to be 1/2. That's the probability of getting candy, plus the probability of a 2 times 1/2 as well. And I'm very sorry, I didn't get that right. That's 1/10 plus, and this is going to be 1/2 over 1/10 plus 1/2 over 10. And really, that's going to be simply 2/10. Do you all agree with that, class? I'm sorry, I didn't miss that. What's the next part?
If no candy is received, what's the probability that the button that never works was the one that was pushed?
All right, y'all following this one? This is a Bayes theorem problem, so how do you cast that one? The probability that no candy is received, correct, class? With me? So now I'm gonna say probability, here it's gonna be on the bottom, I'll just call it no candy received, right? Given that 1 was pulled or what?
If no candy is received, what's the probability the button that never works was the one that was pushed?
0.
Yeah.
Right. So it's, if no candy is received, then probability that the actual probability is 0 is pushed. I'm not sure how to put that, but I'll just say 0 pressed. Well, if you get something representative of the wording, and I'm trying to do that, you almost know, if this is Bayes' theorem, whatever is down here, follow me on this? The probability of no candy goes in front of this, so it's probability of no candy. Now on the other side, with Bayes' theorem, you know what? I'm going to invert the process. Do y'all follow me? So on top, it's the probability of a 0 pressed. Right? That's akin to that times the probability. And this would be of no candy given a 0 is pressed. First, I want to make sure everybody agrees with the way I did this statement. And I'll admit, this is not exactly an electrical engineering problem, but it forces you to think rationally and logically about this. All right, so I'm going to take probability of no candy and divide this by, both sides by that. Probability of no candy here. Then, when you look at this, we want this. That's the thing I want. Over here, we have this. Probability of a 0 is pressed would be, now this is, remember, they're all equally likely. So what's that? 1/10, good. Times the probability of 0 is pressed and no candy. It's going to occur. Times 1 over probability of no candy, which is 2/10. So that means it should be 1/2. Do you agree with that, class? One of the things that'll confuse you here, if you think about this, if we get no candy, we know one of these is pressed. Assuming a coin, because any of these pressed, we're going to get candy. So you limit, the possibilities right here. But the thing that'll get you is it looks like if they're all equally likely, the probability of no candy would be 1/3. But because these are the probabilities of a payout, you have to incorporate that into the mix too. And it gets a little more, well, it gets more confusing. All right, that was part B. What's part C?
If candy is received, what's the probability that one of the buttons that work one half of the time was the one that was pushed?
Y'all hear that? So now the probability here, it gives you candy is received, so we got candy. And then it asks the probability that,
One of the one or two was pressed.
yeah, it really, yeah, call it 1, 2 pressed. Get rid of that. I apologize, I'm not being that neat or clear, but in the printout, in the solution I put up there, on OneNote, it's very clear if you look at it, I believe. And nobody has a problem getting on OneNote, right? Because I use that extensively for everything. All right, now for this one, again, we go, and the way I always recommend it, just, this is the probability that candy is received, right? So I multiply this by probability of candy received. And this is going to be, on this side, the probability, this is going to be, basically I take this and I just replace the candy with this. Probability that a 1 or a 2 is pressed. And then, well, actually, go ahead and do this. Then it's going to be times the probability, and here it's going to be a candy received given a 1 or a 2 is pressed. I'm trying to just make sure you see how you can take that word statement and turn it into Bayes' law, Bayes' theorem here. Agreed? All right, I'm going to divide probability of candy over here. And then, everybody agree with that? Now we go ahead and we take what was mathematically stated in the first part, in the beginning of the problem, and complete this, calculate. So the probability of 1 or 2 pressed, that there are 10 buttons,
2 tenths.
2/10 or 1/5, but I'm going to leave it as 2/10 for a reason. Then probability of candy received given a 1 or a 2 is pressed. What is it?
One half.
You're right. If 1 or 2 is pressed, the probability of candy, well, it's not both are pressed. That's the thing I'm trying to say. It's a 1 or a 2, not like the OR gate, both of them occurred. Either a 1 or a 2. You press either of these, the likelihood of getting candy is 1/2. And so this is 1/2. Finally, the probability of candy, keep that. Well, what's the probability of candy? It's really going to be 8/10. It's 1, 1, 1, 1, 1, 1, 1. That's 7 plus a half plus a half, right? Because if they're equal. So that's going to be 1/8. No, I mean, I should say 8/10. My picture. 8/10. And the 10s cancel, these 2s cancel, so I get 1/8. Do you agree with that, class? By the way, was that clear enough from the solution on how to do this? Okay. Meant to be very clear. Next, I want to do one more. I'm not going to linger on this one, but Oh, these are all good problems in 1-7. We'll do 1-7.4. I think I signed that one too. How many games are they playing today?
Two.
What time's the first one start?
Yeah.
I don't know what they're gonna do for the rain out. I really don't.
A fair coin is tossed. If it comes up heads, a single die is rolled. If it comes up tails, 2 dice are rolled. Given the outcome of the dice is 3, given the outcome of the dice is 3, but you do not know whether 1 or 2 dice were rolled, what is the probability that the coin came up heads?
Now, 3 is the sum of either the 2 dice rolled together, like a 1 and a 2 or 2 and a 1, or it's for a single die rolled would be just a 3. That's the whole idea of this problem. So for this one, he's saying a 3 roll given, we're gonna do something about, we're gonna talk about the possible outcomes first. So for this one, if it comes up heads, you roll a single die. So if it comes up heads, you have possibilities of 1 through 6. Do y'all follow me on this? And then if it comes up tails, it's assuming this is a fair coin. Probability of either is the same as 1/2. Then 2 die are rolled. So when you take a look at this, the possible outcomes are 1, are actually going to be
2 to 12, right?
2 to actually 12 if you're adding. Y'all follow me, class? All right, now you've got to break it down to, of these things, what can have 3 as an outcome. That's given, right? 3 is the outcome. For this one, I can have a head and a 3. And if a tail is rolled, I could have a tail. And because they want a 3, it could be a 1 and a 2. And if a tail's rolled, it could be a 2 and a 1. But you can't have a 0 and a 3 because die are always numbered starting at 1 to 6. At least that's an assumption. Everybody agree with this? So if you take a look at this, each one of these outcomes is equally likely, right? So the probability of either one of these, any of these is going to be 1/3. Now the question asks what? The probability that given a 3 is rolled, right? 3 is the outcome. That
The coin was heads.
a heads was rolled. Follow me? So the thing you have to have first is the probability that 3 is an outcome of this, right? Now you got to think about this. The probability of a 3 an outcome. For the first, there's only one possibility, right? Now for the second, there's 2, right? But what's the total space? Because this is what the thing I'm trying to get at.
36.
Pardon me?
36.
Yeah, I'm not going to put them all down, but how did you get it? You're right. You have heads, 1, heads, 2, heads, 3, heads, 6, correct? Then you have tails, 1, 1, tails, 1, 2. Or, I'm sorry, yeah. Tails, and I better do it this way. Tails, 2, 1, and going down here. This is going to have 36 possibilities, correct? Or, wait a second, am I wrong about that? Better be careful. I'm trying to do this in a binary way. If it tails is rolled, we want the total possible outcomes, correct? All right, if you look at this, if a tail is rolled, you're gonna have 1, 1, 1, 2, all the way down to what, 6, 6, correct, class? That's 36, isn't it? You all follow? So this is gonna be 36 possible outcomes. On this one, there's 6 possible outcomes, correct? Now, when you do this problem, when you're doing this problem, I have to take the probability of heads given a 3 is an outcome times probability of 3 as an outcome. I may not need that. Is equal to the probability of a heads roll. I guess I don't need that actually. Times the probability 3 is an outcome given a heads was rolled. Y'all follow me on this? I didn't need that. This is, I was thinking about it. Another problem that could be, you could actually create from this situation, but right now, just this, all right? And by the way, the key thing is making sure you get this right. All right, if you take a look at this, I'll simply divide this by probability as 3 is the outcome. And if that's the case, and I want that bit of information, what is the probability of a head given a 3 was rolled, or 3 was the outcome? Well, the probability of a head is what?
1.5.
And the probability that the 3 was the outcome given a head was rolled is?
1.6.
Over the probability 3 is an outcome?
3 over 42. Is that all? Because you take the entire space.
Yeah, and so it's gonna be what, 6 and 36, right? So I just put, wait a second. For 3 as an outcome, you got 1, 2, 3, 3 over 36, it looks like, right?
It'd be 3 over 42.
Or 42,
The
sorry.
x is 1.
3 over 42. And, because you have, I'm sorry about that, but it's all possible outcomes, correct, class? So for this one, what does it come to? 3/4. So you got what? 112 over 3 times 42. What is that? 3/4. And this is I think this is the most important part, but for total outcomes, you do have to kind of find some way to get a visual or imagine what they could be for this one, because he's mixing coin tosses with dice outcome, and it's a little odd. What's the next part?
That was it.
All right, is everybody with me on this stuff? All right, I got a few things to cover today in the next chapter. Are there any other questions about first chapter? I mean, we did Bernoulli trials. I'm not going to ask you Bernoulli this time for one reason. I don't think you have adequate time with your calculators to do it. You did stuff with Bayes theorem and applications of different spaces. But now what I'm going to do, and I'm not going to use PowerPoint for this, I'm going into the next chapter in the PDF, and this is going to be on something I hinted at, and that's the probability density function. And I'm going to try to be real clear about this. You know how they had the, I was putting up in the PDF, and it's available, the PowerPoint slides, how they had the frequency, the number of times an event occurred, and then they would have the value, like grade value on the bottom, and the number of times people got that. Y'all follow me on this, class? I'm just going to try to sketch this and get to the point here. So, if we take a look And we have something like, this would be grades. You can just watch this, you don't need to write this down. And this is the number of occurrences. It's called number of occurrences. And you get something like if you had 50, a line like that, 60, 70, 80, and you get the idea. But anyway, there's a frequency. You all follow me? Now, one thing you know, if I could sketch something on top of this, like that, a curve, this is a bell curve, a Gaussian curve, I'm trying to represent. If you looked at that, I know that if I integrated under that curve or summed all the numbers, the frequencies, the number of occurrences, I'll get the total number of occurrences in the classroom. Do you agree with that? Then if I have that total number of tests taken, and this is called the frequency of occurrence. If I took the frequency of occurrence, I'm going to say this as best I can, but then I'll show you exactly what I'm trying to get at. If you take this right here, you take the frequency of occurrence and divide it by total number, you're going to get a fractional value. Follow me on this? If the total number is 100, and say there's 50 at a value of 70, so it'd be 1/2 right there. And it really doesn't matter if it's discrete or if it's a continuous type of function. It has no bearing on this. But if you take this and you sum up all the possible values of frequency over total number, you're going to get 1. You all follow me on this? I'm trying to extend this and show you something that's critical, and this is used all the time. There's something we call the probability density function. This one you can take note of. So it's called the probability density function. And what we usually do is you'll see a small p and it'll have PDF. And it will have a function if the variable is x here. Sometimes you'll see small f of x. Doesn't matter what symbol is used. It's called the probability density function. I got to ask you this. How many have heard of this before? The probability density function is used in engineering everywhere. I mean, radar, it's used in VLSI processing because it'll allow you to calculate all sorts of information that becomes critical. Like it'll get your yield rates for a VLSI technology. What percentage of the chips are actually going to work? And this is based on statistics from before. It'll also allow you to calculate basically the expected return on investment from all the money put into the product and all the money you're going to receive. I mean, some of this is statistically a guesswork. You'll take a look at what you're going to make, and it becomes critical. I can't overestimate this. So when you talk about the probability density function, it has some properties and it represents the probability of an event occurring. Now I'll try to get to this and by drawing a little picture of it and then showing you exactly what it means and how it's used. That's my real goal today. So if I talk about this, first of all, here's a typical probability density function. If this is the value of x, and this is the probability density function of x right here, or f of x. If I take a look at that, and I'm using a bell curve here, it doesn't matter what the values are. I take a look at this, the first thing is that if I take the integral from -infinity to infinity of the probability density function of x dx, I get 1. It means the event will occur. If you take from all possible values and you integrate this thing, you're going to get a value of 1. It has to occur. Do y'all follow me? There's nothing about this that is mysterious in any way. The second thing is, if I want the probability markers. Ever since COVID, markers have not been what they once were. I think because they've got a whole bunch of stuff in the shelves, they just pull out. Go to the bookstore and get some going. So the second thing is this: if you want the probability that X is between A and B, now you follow me, I've got a range of values here, between A and B, and I'll give you concrete examples. What that amounts to is simply the integral from A to B of the probability density function, and I can use f of x here, of f of x dx. So that tells you, if you have a probability density function, these are created usually from statistical information. They run a process over and over and over and over. They gather all the statistics, then they create this. So if that's the case, then if I have the probability density function, I can calculate the value of this value x between A and B. Do you follow me? Just try to go along with this one. The final thing is, and then I'll give you an example of it. If this is called the cumulative distribution function, I don't consider it that important. But when we take a look at f of x, this is the cumulative distribution function that I alluded to last time. Somebody bought some, so. That's equal to the integral from minus infinity to x of the probability density function of x dx. This is a good one. You with me, class? And you can think about this, the probability, it's saying that what's the probability of x having a value, or of this, whatever you choose for x, of the value being x or less than x. And one thing for sure, based on that, what is going to be the value of the cumulative distribution function as x goes to infinity, class? Has to be 1. Absolutely has to be 1. By the way, what is the value of the cumulative distribution function if x goes to minus infinity?
0.
Has to be 0. With me on this, class? All right, now, real concrete example. Let me get your quiz. So I'm going to say this, and I'm just going to use words to express it, that the probability of something occurring between A and B is constant. Follow me? So I'm going to draw it up here. I'm going to say if this is A and this is B, we call this axis X. This is the probability density function here. I said it's constant, it means this. Y'all follow me? It's just going to be a constant. This is just for example. Now I don't know what the value of this is. I'll call this value capital C, all right? So based on what I told you, can you tell me how to calculate C for that one? Everything is abstract, right? It's A, B, no hard numbers. How would you do it? Well, we know one thing. The integral of the probability density function, dx, from minus infinity to infinity, or from A to B, is, class?
1.
Has to be 1, right? By definition. Well, since it's a constant, when I integrate a constant from A to B, I simply get that constant times B minus A, and that's 1. Everybody agree with that? All right, so the value of C is just equal to 1 over B minus A. And I can put a value of B of 10, value of A of 5. It doesn't matter. Y'all follow me? It's irrelevant at this point. Now, I'm going to ask you something. Matter of fact, why don't we make it concrete? It seems hard numbers make the points stick better with students. If I say A is 5, B is 10, or the width is going to be 5, what is C going to be? Go ahead, say it. 1/5, right? 1 over quantity, 10 minus 5 is 1/5. If that's 1/5 here, that's great. Now I'm going to ask you a question. So we've got this is 5, and this is 10. This is 1/5. Now I'm going to ask something that this is a real basic problem, but I'm trying to take this in the next logical step and not go too far ahead of everybody. I take a look at this. What is the probability of X, this is a random variable, between 6 and 8? How do you get that? Well, it'd be the integral from the lower limit, correct, class? 6 to the upper limit, 8, of f of x, and f of x is simply 1/5 dx. Y'all follow me? The probability density is a constant. It will vary generally. Most of the time, it's a function of x in some way. All right, that's simply going to be what? That's 2 over 5, right? Correct, class? So what's the probability of it not being between 6 and 8? 3/5, right? We know it's got to be somewhere. So it's one of those things. That's the real concept of this. I'm going to give you problems about this, but the probability density function is, in my opinion, I would rather do that first before the cumulative distribution function. And that's the reason I'm spending time on this right now. All right, class, do me a favor. Let's go, tell you what, why don't you just move behind him? Yeah, right, and then empty this row. And I'm gonna ask something. I'm gonna ask for you guys to move this way and you guys to move this way. Fill up this row and then that row.